Hello, welcome back and welcome to session 2. In this section we will first discuss the link layer. You remember the link layer from the Internet Protocol stack, right? And then we'll discuss the notion of interfaces, which is really essential to understand the workings of the Internet protocols. First of all, why do we begin our discussion at the data link layer? Why not the physical layer? Well, the reason is that Internet protocols do not really care about it. It doesn't mean that the physical layer is unimportant. In fact, without the physical layer, communication is impossible because that's where the real movement of data happens. In some sense, all the other layers stacked up on it are illusions. It's like you think you're talking directly to your friend over the phone, but it's not possible with the real electric signal transported over the copper wire in the telephone network. However, we simply trust the data link layer to deal with whatever happens on the physical layer. It's like in the Amazon book ordering example in session 1, where I did not have to know what airline carried my book over the Pacific Ocean. I let the post office to deal with it. I just don't care. It's just like that. I leave it to data link layer. I mean, not I, but the Internet protocols. And even the data link layer, Internet protocols do not have many things to know about it. As long as the Internet protocols figure out those few things about the given data link layer, that's enough to connect a given link layer technology to the Internet. So we are going to forget about the physical layer in this course from now on. In session 1, we learned that the net in the word Internet means all kinds of incompatible communication technologies. However, it doesn't mean that they cannot be used in communication without IP's help. On the contrary, there's no problem for two computers on the same technology to talk to each other. For instance, if they are connected to the same Ethernet segment, they can communicate without any problem. The problem, however, is that such communication can only be local. No single communication technology can cover the entire globe. That's where the Internet comes in, to connect these incompatible technologies together and form a single global network. Now, from the perspective of IP, these various communication technologies are just links. Okay, so link is an abstraction. We learned that in session 1, right? So when you say that IP considers these various communication technologies as links, it means that IP is abstracting them and ignoring, unnecessary details that happen on the link layer. So IP weaves them into the Internet, and to make it happen, although IP doesn't have to know a lot about the details of the given link layer, it should know a few things about them. First of all, there are two types of link layer technologies. One is point-to-point type links that connects one machine to another machine, and the other is shared medium type links, where on the same link there are many machines connected. Regardless of the types, however, the link layer technologies perform a few common functions. The first is called framing, which structures a group of bits into a unit of transmission over the given link. Grouping the bits into the unit called the frame makes it much easier to manage the communication over the link. In particular, we can make the error control more efficient. The error control here aims at recovering the frame when some of the bits are corrupted or even lost on the link. There's another control called flow control. It controls the rate of data flow so that the receiver is not overwhelmed by the data that the sender transmits. Here as well, the unit of control is the frame. Finally, in the shared medium type link, we have one more control, which is the medium access control, or MAC in short. As the link is shared by multiple computers in shared medium type link, there should be some rules to guarantee the fairness and efficiency in competition by the multiple computers connected to the shared medium. Well, as for IP, error control and flow control are the details that it doesn't have to know. So it doesn't care about error control and flow control. Data link layer should be able to handle them and make it transparent to IP. Only some information on the framing and MAC are necessary for IP. In particular, the MAC address is something that IP should know about the computer connected to a shared medium type link. Let's talk about the framing first. Among the framing and MAC, let's talk about the framing first. In case of shared medium, I said that MAC addresses are of interest to IP. And here is one example of link layer frame, which is from the Ethernet. In case of shared medium like Ethernet, MAC addresses will appear in the header of a link layer frame. As you can see, there are two MAC addresses, one from the sender and the other one for the receiver. And there is this payload which carries the IP datagram. Remember the cabin from that Trans-Siberian Railroad example. In the Ethernet header, there is a very important field called a payload type. In other technologies, the field is called by other names, but their function is the same. It identifies the payload, namely which network layer protocol gave it to this link layer to deliver. In case the payload is IP, for example, the payload type in the Ethernet frame is 0800 in hexadecimal value. Finally, there at the end of the frame, usually there is a trailer that is also called a frame check sequence. And in almost all technologies, it is the cyclic redundancy check value, or CRC. The CRC is an interesting technology in itself, but we are not going to discuss it because it's too low level. Now let's talk a little more about the type of links. The first one is the shared medium type links, such as the Ethernet and Wi-Fi. They use MAC addresses, and it is very important that IP knows about it, which we will see later. For instance, here is my smartphone, which has a Wi-Fi link. Okay, and this is what the IP on my smartphone knows about the Wi-Fi link that connects it to a wireless access point. It's not just my smartphone. All of your smartphones, when using internet through Wi-Fi, has this. We talked about the locations of the protocol layers, and since we are talking about IP, this is in the kernel of the smartphone. Okay, so the operating system is Android in my smartphone. So this whole thing is inside the Android kernel. By the way, this information can be obtained by executing a command called the fconfig, which means interface configuration on Android system. Well, there are many cryptic words and numbers here, but look at the word broadcast here, which means that this link is a broadcast type link or shared medium type link. Okay, Wi-Fi is indeed a shared medium type link, and the name of the link is WLAN 0, which obviously means wireless LAN number 0. And what about the point-to-point type link? On the same smartphone, I can also get this information about my LTE link. The LTE link is a point-to-point link, at least logically. The ifconfig output indeed tells us that this is a point-to-point link. There are other point-to-point type link layer communication technologies, such as PPP here. Okay, so far we talked about what IP should know about the link layer technologies. Now let's turn the table and think about what the link layer technologies should do to connect themselves to the internet. For a link layer technology to be used in the internet, there are three things it should provide to IP. First, it should be able to say that it is carrying the IP datagram in the payload, in its frame. We saw earlier that in Ethernet there is this Ethernet type field that can identify the IP payload. Second, if it is a shared medium type link, it should support the translation between the IP address and the matching MAC address. Third, it should provide so-called a management information base, or MIB, or MIB, for remote management over the internet. As to the ARP and the network management, we will learn in later sessions in this semester. Okay, so let's first talk about the encapsulation. Okay, the first entry here. The first frame format here on top is from the Ethernet with a type or ether type field that identifies the IP payload by the hexadecimal value of 0800. Of course, Ethernet can carry other types of payload than IP, so the type field can have other values as well. For instance, if it is 0806, the payload is from the address resolution protocol, which is related to this thing, address resolution protocol. The second format here is used by the point-to-point protocol. We mentioned the point-to-point protocol here, remember? Okay, so it's from PPP. Although the name of the field is different, so it's called protocol now, this field also serves the same purpose. It identifies the type of the payload here. If it is 0021, it means this part contains an IP datagram. The third format is from the Wi-Fi. It's a little bit different from the other two, that there is one more header in the starting part of the payload, which shows here. If the type field, one of the fields in this so-called LLC snap header located here, the type field, if it is 0800, it means that the rest of the payload contains an IP datagram. Like this, the link layer protocols must be able to tell the receiver that it is carrying an IP datagram. Then the receiving link layer protocol can deliver it to IP. So this is the first thing that a link layer protocol that wants to be used by internet should provide. There is one more thing in this picture that I need to talk about. It is the size of the payload field or data field. In case of Ethernet, you can see that the maximum size is 1500 bytes. Therefore, the IP datagram that can be carried on Ethernet cannot have a larger size than this. For PPP, it's also 1500. For Wi-Fi, it's 2304 bytes. Like this, the maximum payload sizes vary across link layer technologies, and we call them the maximum transmission unit size, or MTU size. If an IP datagram is larger than the MTU size of the link, inevitably the IP datagram should be fragmented first so that each fragment fits in the link layer frame. We saw in session 1 that I need to go through 26 links to reach the website at Pisa University. If I want to avoid the fragmentation of my IP datagram, the datagram should be smaller than the smallest MTU size of the 26 links. The smallest MTU size of the communication path, by the way, is called the path MTU size. We will learn later why this size matters. One thing I can tell you now is that fragmentation is something that is considered harmful in the internet. It makes life hard for the routers. That's why, and you will understand once we get to the point where we discuss the MTU issue again in the later part of the course. Well, this is the cumulative fraction of the packet sizes in the internet. So this is packet size, and this is the cumulative fraction. You can see that many are very small, less than 100 bytes. There is another jump at 576, and finally there is a huge jump again towards 1500 bytes. The graph is from year 2008, so the picture might have changed a little. Namely, the 576 byte jump is not there anymore. And the small packets are from Transmission Control Protocol, or TCP in short, which we'll discuss later. But what is most important in this picture is that there is a huge jump towards 1500 bytes. This is due to the huge popularity of the Ethernet technology, which has the MTU size of 1500 bytes. Even if there are other technologies that have larger MTU sizes, say the Wi-Fi with 2304 bytes as the MTU size, it is highly likely that there is at least one Ethernet link on the path. Any IP datagram larger than the Ethernet MTU size, therefore, will be fragmented. So that's why we do not see packet sizes larger than 1500 inside the Internet. On the other hand, there are not many popular link layer technologies that use smaller MTU sizes. As link layer technologies evolve, they get faster, and the rule of thumb is that faster technologies use larger packet sizes. So 1500 is the minimum MTU size these days, and it's from the Ethernet.